Hello there, welcome to the wonderful world of RF and electronics engineering. On the bench is a microwave modules RF power amplifier. We're going to go through and do some testing and where necessary repairs. You join me what is after the main part of the video has been filmed, so what's coming up will give you a good demonstration of what we're going to do today. And we're going to use various pieces of test equipment that you see behind here to test this amplifier thoroughly, including a directional coupler. We're also going to get instruction from the technical manager, and we've got various measurements we're going to do with harmonics and RF power, and what you'll see in the upcoming video may help you with confidence when you're doing measurements yourself with RF power amplifiers, how to make harmonic measurements and also measure RF power correctly. And we'll go through the circuit theory as well on the product. We'll analyze its function and go through all the alignment process, as well as obviously the supporting technical information. So stay with it. The upcoming video I think you'll find very interesting, and we will progress on to that now. Thank you. Hello there, thank you for joining me again today. On the bench for repair is a Microwave Modules Limited UHF linear power amplifier. It does up to 100 watts on 432 megahertz. This came to me, I acquired this fairly recently myself through a radio convention that I went to, and there's a label on the top that says that it doesn't transmit, it's not working. And as we can see there, and it rattles as well. There's something loose inside. When we move it, you can hear it. So there's something wrong there. Now if we have a look in the rear, we've got what is the output is a type N connector. The fuse holder has got the central part of the fuse holder part that holds the cartridge fuse missing. We've got an RCA plug here, which is used for if we're going to use this amplifier in conjunction with a Morse key or an external transmitter that uses a manual keying output. And then we've got here a TNC RF connector for the input RF. Why they've done that I'm not sure, but anyway, that's what we've got there. We've got this thick supply cable. Feeling in here, I think they've put some ferrite beads in around the wires and then heat shrink the wires on the top there. We've got about a metre of cable which is terminated in these two spade connectors. So I think what we'll do, I'm not going to power it up because if there's bits rattling about inside, and obviously somebody's been in it because this fuse holder's missing, or maybe it's just been lost, so we'll verify that, and we'll take it apart and have a look inside, see how it's designed, try and repair it and get it working. It's obviously quite an old amplifier, probably going on for 20 to 30 years old, probably around about that era. Microwave Modules was a company here in the UK that was around a long time ago. They made a lot of transverter modules, up and down converters. They made RF amplifiers, all kinds of things in their product portfolio. So it's a well-renowned brand here, particularly in the UK and possibly around the world. But it obviously produces quite a bit of output power. 100 watts at 432 megahertz UHF is quite an achievement, really, for such a small device. So yeah, let's have a look inside and see how it's constructed. Okay, we've got the lid off now on the bottom. Real good piece of metal that's not cheap tin rubbish. I mean, that's good and proper plate steel is that, you know, well constructed is that. So okay, having a look at the internals of the amplifier, I can see straight away we've got the remnants of something down here, which is this blue stuff down here. Looks like as if something's popped, exploded and then shedded its contents all over. Looks like a tantalum capacitor, would you believe? So perhaps we've got a blown, or had a blown, capacitor inside here. Now, looking at the architecture, it's quite common on ham radio power amplifiers, is this architecture that we see before us. We have here on the TNC input a little PCB with some components on it. Now, it's imperative really when we're dealing with the signal coming in that we attenuate it so it doesn't overdrive the amplifier stages, because obviously we typically might be using, say, a handheld radio that transmits at 5 watts, or a mobile radio that transmits at maybe 10 watts or something like that. So we, you know, obviously need to attenuate that down before it reaches the driver transistor. And typically that means having to introduce some kind of a pi attenuator. Now, unlike professional radio equipment that uses a proper 10, 20, whatever, 6 dB pad or 3 dB pad, whatever, that's one of the substrate resistors that I've shown on the channel before. The type of thing that you find in radio communication test instruments, things like that, they're very expensive to buy, are these pad attenuators that can stand, you know, typically tens, if not into the hundreds of watts, and they're bolted to the heatsink. They look very similar to an RF power transistor really, but a square one with a leg on either side. And you'll have seen those on my channel, and I've got a box of them here somewhere, which if I find one, I'll show you on this video. But rather than go to that expense, they've chosen these power resistors here, which are obviously rated at a few watts each. Now they do have a rating. It says the one is 150 ohm and the other's 33. And then there's another resistor here at the top of it, sandwiched between the relay and the larger resistors, which then goes down to RF ground. So that's forming a pi attenuator. So obviously we've got that sort of arrangement. Now, on that little circuit board as well, there's a few components on there. And what we have to do when we're transmitting into an amplifier like this is we need to detect on the input socket the presence of RF. And on most amplifiers that's achieved by having a diode that senses the RF coming in on the input socket, and then that then goes to the a smoothing capacitor on its output with an RFC radio frequency choke. And then the DC level then is sniffed off that and fed to what is a control circuit, which the duty of the control circuit is to switch the antenna path from the receive mode into transmit, and then connect the signals that are coming into the amplifier and transmit to the amplifiers, and then ultimately you know, to amplify the signal up and reconnect it back out to the end socket on the rear. However, when there's no RF signal present for transmission, then the relay is switching a configuration where the input socket and the output socket are essentially connected together. And so that allows received signals then to enter the amplifier output socket and then be connected to the amplifier input socket, isolated from the rest of the amplifier. So there's a direct connection between the sockets. So that allows a radio receiver to operate then, because if that wasn't there, then obviously the transistor circuitry would obviously prevent any received signal from going back in reverse, if you like, to the input socket. So that's the general configuration. That's why we have two RF relays. We've got essentially one on the output here, this large relay, which is a mechanical switch relay with this plunger. And that connects the high-powered 100 watts UHF signal from the output of the amplifier to the antenna socket, whilst disconnecting the connection from this socket. There'll be one side of it has a connection to the input socket direct, and the other side here, the output socket, will be connected. So in receive mode, in this current state that the relay is in, they'll both be connected together, the input and output socket. The moment we're going to transmit and that plunger goes in, then it'll disconnect these two from being connected, it'll break the connection for the input and output socket. And then what it will do, it will connect the output of the amplifier to the output socket. Likewise, the input relay, which is here, this small one, will be disconnected from providing a signal to this, and it will then obviously isolate this path and connect the RF signal that comes in through these resistors then obviously onto this transmission line here. And so that's basically how that works. Now, it looks like on this circuit board here, I can't see a diode. I'm not sure if this is one, an old school diode. It may be, it may not be, but there's definitely, when we look at the wiring loom here that goes under the board, this sort of goes under the board to the rear of the unit, and it pops out here in this corner, and we've got a wire which looks like as if it goes off. It's quite difficult to see. There's like a black wire solders to this PCB down there, and I'll just zoom in a little, maybe might be able to. Let's have a look. Might be able to see there's a brown wire and a black wire. The black wire solders to this PCB, which is where the RF input comes in. So this has got to be able to sense the presence of RF and then give an output on that black lead as a DC level. So there must be some kind of rectification, RF rectification taking place on this board to give a DC output on that black wire, which then goes to the controller board at the front. There's also a brown wire, which as you can see goes into this red shrouding. If we just have a look here, it just disappears off into this red sort of protective jacket and then goes to the RCA socket there, and as you can see there's a little ferrite bead on it as well, and that solders straight to the middle of this RCA for an external keyer, so that can manually control the switching of the input and outputs. So when we've gone through detecting and the switching, then obviously to switch the RF paths, the RF signal coming through these pi attenuator resistors is obviously dropped from say 5 watts to maybe 1 watt. It then enters this strip line, this tuned strip line, which has got a variable capacitor across it. We appear to have a bias resistor here, and obviously it hits then this MRF 646 RF power transistor, which then obviously amplifies it. Now, looking at the biasing arrangement, it looks like as if the bias pot for this is set by that potentiometer there, and that's where we get the DC bias fed to this track here to feed this transistor. So obviously this being a biased amplifier can operate in AM and SSB modes, in other words in class AB mode, because it's getting bias, and not just class C for FM. If it was class C, it wouldn't have a bias arrangement, it would just be as you see now but without this bit, and thus it would only be suitable for FM or CW operation, not AM or SSB. So this presence of this bias circuit indicates that it's a class AB suitable for use with SSB and AM. Then we've got the collector, which is fed via radio frequency choke, which we can see here, and this radio frequency choke then has got a capacitor, which is this silver square thing here. We've got another RFC, then to some more filtering, and then we've got the main supply wire to the first stage amplifier fed from this red wire. We've got a couple of capacitors soldered in here or there, and mainly resistors, look old school caps and things. We've got another capacitor on the output here, this plated capacitor. You might be able to just see that, make that out there. So this plated capacitor then tunes the output of this device. Then we go through another strip line into basically a combiner architecture on the input to the two power amplifier transistors. Very similar arrangement to what we had when we looked at the Kenwood TS2000 ham radio transceiver power amplifier for VHF, where we had the effectively quarter wave stubs, tune stubs coming into the transistors. Again, we've got a dual biasing arrangement here, two separate bias pots to then provide biasing via these two resistors to the base of these bipolar RF power transistors. And then of course, after the bias has been applied, we've got what is a collector, which is again part of this output. Notice the thickness of the tracks now increase somewhat from the input dimensions of the track, and we have then on the output of this connected when the signal reaches here, and this is the DC feed point for the collector volts for the main supply, which is under this wiring loom here. You can just see like a little filter. So there's DC volt supplied by a red wire, which comes from the rear fuse holder to there. That then goes through another radio frequency choke, smoothed by again another capacitor, which is, these capacitors are mainly for radio frequency choking off. So essentially it's like a bit like a bias T in a way, the way that operates, where we've got some inductance, lumped inductance, and then a capacitor which is specifically chosen to prevent any RF energy coming back onto the supply lines to the device. So there'll be numerous capacitors scattered about on that supply line, as we can see under the wiring loom, as well as this capacitor, to prevent any RF from getting back. So the RFC here supplies DC power on this point here to the collector of both transistors, the output of which is the RF is superimposed on this as well, and obviously we get to this feed through capacitor here. This is a DC block, in other words. So basically the way this works is that the DC potential, full supply to potential is on here, obviously because it's fed by this RFC, so we need to get rid of the DC and just allow the RF signal to pass. So this is the main series capacitor, which then blocks the DC and allows the RF to come off, which then allows it to decouple onto this track again, and then that feeds into this relay. Now you'll notice as well, if you look very carefully at that track, if I can just zoom in a little bit and just come in, you'll notice there is a another track running parallel with it, which you can just see there. Now that's a directional coupler, which is used to sense the output VSWR. So if the our transmitter amplified output runs into an unmatched load or a high VSWR, this is part of an APC, an automatic power control circuit, which will then limit the RF power to the device by reducing the DC control voltage to this transistor here. Now if we look further back, which is this DC supply rail here that comes from this red wire, that in turn I theorise will be controlled from one of these power transistors that's bolted to the chassis. So this will essentially be a variable control feature for controlling the DC level to this driver transistor, and thus by, if we detect for example high VSWR, then the voltage will be reduced to this, and thus its RF gain will be reduced, and it'll not then drive the amplifier to such a state where it could damage the transistors with a high reflected signal coming back into them. So that's what these are for. And obviously on the front I think there's a possibility of a, is it on or sometimes there's a high and low power switch on them, but there isn't on this. But you can control the RF power amplifier's output via these transistors. We've got as well a heat temperature sensor, which is bolted to the heat sink, which is what this device is, sensing the temperature of the heat sink. So if the amplifier gets too hot, it can shut off the power to the driver transistor, and thus it will not then amplify, and then it'll cool down. And it's got a little IC here to control it, and some other old school capacitors and things. And likewise on the output again, where we just got to here early after the directional coupler, we then have the output of this mechanically switched relay connecting to this track here. It looks like a technical manager might be joining us in a minute to give us some technical advice. Anyway, it comes out of this track and then goes up to the other connection there. This relay will have 3 contacts on it. Basically, it'll have a common which goes off to the antenna socket on the rear. If you like, the top connection will go to this track here, and the bottom connection will go off then to this relay here. So all the high power RF component is switched here, and then when obviously the amplifier is not in use and it clicks back into receive mode, essentially it will be these 2 connections here that will be connected together in the relay. So this track, and then the track that you can't see, it's just hidden underneath the board, it's not something that's visible from the top, but there'll be a track connecting between those 2 relays. Likewise, under the relay on the right, which is screened by this ground connection here that's soldered to the casing of the relay, on the underside will be a connection that goes to this socket, as well as then another connection, again the 3-terminal concept as per the legend on the can of the relay. One side will go to this pi attenuator, the other side will connect up to this relay, which, as I've just explained, will connect back to this track and then to this socket. So essentially these 2 sockets are connected together whenever there's no RF being detected. So there's a few things to test. Obviously we've got a tantalum capacitor that seems to have blown, and this is why we've got these little pieces here. So it'll be interesting to find out what's gone there. Looking at the fuse holder at the bottom, looks like there's been some interesting thing going on there, because we've got underneath here, if I just move that out of the way, you could probably see somebody's desoldered the wire that will connect on this terminal, which is just flapping about in the breeze, and they seem to have bridged it out. So this feed through capacitor here, which is obviously the main DC input, would normally connect to the perhaps the middle terminal there, which is just underneath there. That wire that's looped there would desolder and connect there probably. The larger cables then would connect where they are now. So somebody's bridged that out instead of replacing the fuse holder. So we've got plenty of fuse holders. We're able to replace that a bit later if we get it going. And so yeah, that's interesting. Now it looks to me like as if there's been some component change. These look remarkably shiny, these tantalum capacitors, and this one here and that one, and if I move that away, it's left a rather dirty mark on this capacitor there. I'm not sure if that's, I think the tantalum that was originally there went fizz bang or something's gone, but it doesn't look too happy now, because if we turn it round, I think you'll be able to see it's got a bit of a scab on it just there, look. So you can see that black dot that's on it, and I don't know if it's just flux residue or something. It might be burning up from inside, I'm not sure, or it could just be a bit of flux or something that's spat onto it. But sometimes they go short internally, and then before they do burst into flames like a Roman candle, they do sometimes start to discolour, and you get like a dark spot on them. But they look new to me. They look new. So I think originally the capacitors that were there went fizz bang, and which is the reason why we've got all this debris down in the bottom there, which you can just see. It's not been cleared out, and I think that's probably what's happened there. So yeah, interesting. So I think one of the first tests we need to do, because obviously I'm hoping these transistors are okay, hoping the devices themselves are not blown, because for some of these capacitors, sometimes with it being a radio power amplifier, it has been known for, and with a fuse holder being tampered with as well. I can't see a reverse. There is a reverse protection diode, which is right down at the bottom, down there. I'm sort of a little worried, really. You can just see the reverse protection diode there. I'm hoping that it's not being reverse polarized, and then obviously, you know, it could cause severe damage then to the whole unit, including, you know, some of these expensive devices. Who knows? Something strange has gone on with the power. For the tanks to have blown, which is on the main supply line, because that is where the supply for the radio frequency choke to the collectors of both these bipolar transistors originates, as well as the fuse holder to have been ravaged. It could be that it's either been over voltaged and that's why it's popped those tanks, or it could be it's reverse poled. Somebody's got positive and negative the wrong way around on the power supply, and it's jiggered it up, you know. So there's a few things we need to test. I need to check as well that it detects RF. I can't see a diode on that board, but this might be an old school diode. That looks more like a resistor or capacitor to me. There could be something hidden on the other side of the board as well. I would suspect that's a capacitor, but I'll test it in a moment. I can't see a diode, a glass diode, on this part of the PCB, but there would have to be a diode there to rectify the RF for this black wire to pick it up. I haven't got a diagram for this amplifier either, so it's going to be interesting. Anyway, at least these resistors aren't burned out, which shows that it's not being driven with too much RF power. The relays will probably work. I don't see them having a fault. It's very rare, unless the contacts are dirty, but these are serviceable anyway, this particular one. So I think what we'll do, I'll put it on a current limited power supply at first, so that we, you know, if there is a short, it's not going to burst into flames, rather than putting it straight onto a 40 amp power supply and, you know, obviously burning it out. And then we'll do some testing. Might give it an RF drive signal as well, and connect the output to the radio test set, and take it from there. See what we can get out of it, or what it does, or more to the point, what it doesn't do. Yeah, I was just looking for this diode detector on the RF power sensor on the antenna, on the input socket to the power amplifier. I couldn't see it on the top. If you just zoom in a little bit, and you might be able to see down there, there's a capacitor that goes between the inner of the TNC RF socket, which is just there, and that capacitor there then bridges across to here. Then there's nothing else visible apart from this capacitor here, which this black wire solders onto there. So I thought, where's the diode? Anyway, I found out where the diode is. It's hidden. It's hidden. So if I just try and move the camera, I might be able to see just down here. Always, it's a pain in the ass to try and demonstrate it, but just have a look down there. You might be able to see, sandwiched on the board between the rear case and the PCB, there's two glass diodes down there. So they are the there could be something like OA91s, OA61, something like that. They are the RF rectifiers. So naturally the capacitor decouples the RF to those two glass diodes, and then obviously the output of the diodes is rectified by that capacitor that you can see just down at the bottom before it's connected off to this black wire. So that proves obviously that the transmitter detect is there. Another thing as well that I just wanted to mention is that of course when the amplifier's in a switched off state or powered down state, we still want obviously an RF signal to be able to pass both in receive and transmit mode from the drive device between the input socket and the output socket without any interference or hindrance. So that's why we need to disconnect and isolate the circuit here, including the pi attenuators and all the other gubbins inside, from having any attenuation properties on the receive signal as well as the transmit side. So if we've got a 5-watt handheld, while the amplifier is powered down and not in use, we want that 5 watts to make it to this side to then go out to the antenna. Likewise, any receive signals to come in and then go obviously to the antenna input or the RF input socket. And we don't want it going via these attenuator resistors, because obviously then that would attenuate the receive signal as well. So it's got to have that clean connection between both input and output socket. So that just gives a little rundown of that. Right, we've made connection now on the rear of the unit. We're basically using the Kenwood TS2000 that we recently repaired on this channel as a UHF drive source. We've set the RF power down to, obviously it goes up to, quite a lot of power, so we've set it to 50 watts on FM, 5 watts on FM with 433.225 in that case. We've got the output of that of the radio transceiver into the right side there of the amplifier. The left side of the amplifier there, which is the output, is connected up to the Marconi radio test set. So what I'm looking to do, because we've got two power supplies running, the top power supply there runs the radio, the smaller one, and the bottom one is connecting to the amplifier, which can provide up to a maximum of about 40 amps. I'm expecting this amplifier to draw a good 20 amps if it's doing 100 watts at least, so that's why we need the high current there. So in its current state, what I'm looking to do now is, while it's switched off, is first of all let's just switch it on to see whether there's any short circuits or any funny business going off, and there isn't. So that's switching it off, that's switching it on, so there's no short circuits. So we can have a look now while it's in the off mode to see whether the RF signal passes correctly through to from right to left and then goes out to the radio test set. So although we're transmitting at 5 watts, if I just zoom in onto here, onto our RF meter, see if I can get this set up. Sorry about the creaky noises. Okay, so if I transmit now on the radio at 5 watts, we should be getting some TX power there. So I just select TX test on here. And 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. So we're getting about 3.926 watts there roughly. So 3.9 watts in the top right. So that proves that the amplifier is in pass-through mode, which then understandably indicates that the RF path between the input and output sockets there. So what we'll do now is we'll flick the amplifier to on, and we'll just have a look and see how much output power we can get from it, see if it comes on. So when I press the transmit button now, we should be getting something, and we're getting some current drawn on the power supply as well. And there you can see the needle moving as I key up the transmitter. So I just need to see now what the transmit power is on this meter. So let's have a look, see whether we can see what the TX power is. Right, so we'll transmit now. 70 watts at 5 watts. So just unkeyed. I'll just turn the volume down on the test set, and then 1 2 3 4 5 5 4 3 2 1. So that's 69 70 watts. Seems to be operating. Seems to be fine. It's drawing some considerable RF, well, current anyway, definitely. So 1 2 1 2 1 2 1 2 1 2. I'll put it into AM mode and turn the power down to 5 watts again. Let's have a look. 1 2 3 4 5 5 4 3 2 1. 1 2 1 2. Put the mod type at AM. 1 2 3 4 5 5 4 3 2 1. This is a test. 1 2 3 4 5 5 4 3 2 1. A good sort of we know mod 60 watts or thereabouts. 1 2 3 4 5 5 4 3 2 1 5. What about sidebands? LSB, USB mode. Go on to RF test, single sideband test, and we're on upper sideband on the radio, so we'll switch to upper sideband. Let's see what we get. 5 watts again. 1 2 3 4 5 5 2 2 2 2 2 2 2 2 3 4 5. So we're getting some power there. I can see the current meter on the power supply jumping up and down with the mod as well. So sideband's working, it's detecting the RF there as well on sideband. So AM, FM, sideband modes work perfectly through the amplifier. Now we could adjust perhaps the biasing to see whether we can get more RF output power from it. That's possible. But I'll just see if I can do a bit of research online to see whether I can find a manual for it that will give us a correct alignment instruction. So back soon. Okay, we've had some information here from Microwave Modules Limited for this MML 432 100 watt amplifier UHF. As it says, quite clear, 100 watts minimum output at 10 dB maximum gain. It says fully protected against poor load, VSWR overheating, excessive or reverse supply rails. Equipped with an RF Vox, voice operated RF switch and manual override. Supplied with power lead and all connectors. So here it outlines the specification again, which we've just gone through there. It talks about power requirements: 12.5 volt nominal at 20 amps for 100 watts output, 13.8 volts DC maximum. Bandwidth is 435 megahertz plus or minus 15 megahertz with a minus 1 dB compression. 10 watts nominal input power for 100 watts output, which is interesting because we were driving it with 5 watts and it gave out 70 watts more or less. So it says a solid state 432 MHz linear power amplifier MML 432-100 is intended for use with any existing 432 MHz equipment having output power of 10 watts. When used in conjunction with such a drive source, this linear amplifier will provide a power output of 100 watts minimum. The inclusion of the latest state-of-the-art power transistors, each of the final transistors being rated at 145 watt dissipation, guarantees a highly reliable and ultralinear unit which is suitable for all modes of operation: SSB, FM, AM, CW, RTTY, which is RTTY, and TV. The amplifier utilises recently developed matching techniques which allow safe operation even when improperly subjected to simultaneously to 50% overdrive and a supply voltage of 15 volts. However, as a further safeguard against damage to the final transistors, the following protection circuitry has been included to shut down the unit in cases of poor load VSWR, overheating and excessive or reverse supply rails. So in terms of the high VSWR, it says the amplifier will automatically shut down into the straight through mode should the sensing circuitry detect a load VSWR of worse than 2.5 to 1 at the antenna socket. The mode of shutdown will be displayed by the illumination of an LED status light on the front panel. The sensing circuit will test for an improvement in the load VSWR every 8 seconds. When the load VSWR returns to less than 2 to 5 to 1 ratio, the sensing circuitry will allow the unit to return to normal operation. In case of thermal issues, should the heatsink temperature reach 65 degrees C or more, the amplifier will automatically shut down into the straight through mode until the heatsink falls well below this temperature. This mode of shutdown will be indicated by the illumination of an LED status light on the front panel. All the voltage and reverse polarity. The incorporation of a crowbar circuit protects the transistors against reverse polarity or an excessive supply voltage. This will automatically shut down the unit should the supply voltage exceed 15 volts or should the supply be reversed. By means of an internal RF Vox circuit, the linear will automatically switch into transmit when 432 MHz drive is applied to the input socket. However, this facility may be overridden by the application of an earth to the phono socket located on the rear panel. This may be achieved by connection of the transceiver PTT switching line. An integrated circuit network provides a well-regulated bias supply for the final transistors, and each transistor is individually thermally tracked against ambient temperature variation and operational temperature rise. All RF circuitry is constructed on high-quality double-sided Teflon PC board, and the use of broadband strip line techniques gives a unit a bandwidth of 420 to 450 MHz without need to retune. The unit is housed in a highly durable black steel case. RF input and output sockets are located on the rear panel together with the 12-volt supply fuse and the push-to-talk line phono socket. Unit is supplied fitted with a 12-volt supply cable, plugs for both input and output, etc. And it waffles on about that. So, we've got a diagram. How useful. Let's have a look and see what it says. What's this then? VSWR thermal shutdown detail. So it looks like as if bit of a circuit there. VSWR input into the IC and VSWR bias RV1. This looks like, what's this then? Vox relay and bias detail. Vox input, PTT and inhibit inputs into there, relay 1, that's that. Excuse me for coughing. Yeah, so that's the TXRX input. That's that print layout as we were looking at earlier with the transistor. So we've got a relay here, relay 1, which is that small steel can relay, which is obviously this relay there, that small one, and then that's relay 1 and that's relay 2. So just have a look at that again in slightly more detail and get the camera to stop moving. So again, when in receive mode, as in no transmit, then the TXRX port for the transceiver input connects via relay 1 and relay 2 to then the aerial socket on the output. Obviously this strip line here is the high powered 100 watts UHF amplified signal, so this would switch to that position to link those two together in transmit mode, and likewise this would switch to this point here, so it would flick across there. So the input power for the transmitter that we're obviously wishing to amplify be connected then to this pi attenuator resistor network for it to be reduced. Goes through a capacitor, then onto this strip line to the base of this transistor, which is the driver. And again, so that more or less follows suit with what we've got. We've got the bias circuitry here, variable resistor, setting the bias, RFC radio frequency chokes to apply bias voltage here onto this transistor, and then naturally we've got the radio frequency choke present here for the collector supply voltage, the main current and voltage supply, which is derived onto this strip line here, L2. And we've got a variable cap, which is that plated RF capacitor I showed you earlier, which is stood on the board. Another decoupling cap, obviously DC block, then onto L3, two more capacitors then feeding in RF signaling, obviously phase relationship to both T3 and T2 transistors. Again, biasing network here, which then supplies bias for the class AB, and then we've obviously got temperature compensation diodes, biasing arrangement of potentiometer here, usual thing, another potentiometer for setting things up. So that's that. Again, the main 12 volt supply rail there comes in to this radio frequency choke, 10 and 9 there, and then connects directly onto what is L8, this print, which then supplies collector voltage to the transistors. So that's that part of the amplifier. I'm just trying to find the circuit now that's connected to this strip line on the RF socket at the rear, where it's rectifying the RF, so it needs to sense that first. So we'll just have a look and see if we can find that. But because it talks about a Vox input there, relay control. Just looking to see if there's a circuit diagram of that showing those, which don't appear to be able to see. Don't think they've included it on this diagram. There's what we were looking at earlier on this PCB, which is at the rear down there. So that PCB obviously rectifies the RF that's coming in from the source transmitter to then enable the transmitter to come on. So I'm not sure where that is, to be honest with you, on this diagram. I can't see it because it just says there VSWR input, and then on the next diagram talks about the Vox input. So obviously this is the supply voltage, if you like, from the rectified RF that's coming in. When I say it's a supply voltage, it's a signal coming in and at a DC level from the PCB that solders onto this track here. It doesn't show it there, you see. So yeah, it might be an extra page on the manual that wasn't copied on this thing, but still it's a good explanation of the device. So that's pretty good. So I think what we'll do now, we'll just set the radio to 10 watts. So it's now doing 10 watts, and then what we'll do, we'll just wake the Marconi up, and let's see whether we can get 100 watts out of it. And you never know, maybe, possibly. I think what I'll do, I'll just reset the test set because it was trapped in USB mode, so let's just go on to that. I'll put the radio into CW mode as well, so when I next transmit at 10 watts input, let's see whether we can get 100 watts out. Doesn't appear that there's any bias instructions or setup instructions in this manual anyway, so let's see if it does 100 watts. Okay, so we'll go on to TX. We'll do, I'll set the radio up to sort of see if I can get it up to spot frequency 433.500 megahertz or thereabouts, and then we know what we're dealing with then, and I'll put that in. So TX frequency 433.5 megahertz, so that's on there. Right, let's see what happens when we key up with 10 watts drive. Right, it's drawing a good 20 amps. There we are, look. It went up to 100 watts momentarily, but it settled at 90 watts. So it's not far off its rated power then. Let's try again. So it went up to 106 watts. Well, it's drawing about 24 amps according to the power supply. If I just drop it down to 5 watts, 62 watts, put it up to 10, it's 88 watts, call it. So that's pretty good. So I'm happy with that, to be honest with you. I could try 435 megahertz and just see whether that roughly can get up there. Let's have a look. See whether we can move its frequency. I think there must be an easier way of doing it on this radio. I've not quite mastered this radio. We'll try it on 434 megahertz first, just to see whether I'll put it in auto tune. 434 megahertz. Right, so I've set the radio up now to 434 megahertz dead, and we'll just go to auto tune on there. We start at 5 watts drive, and we're getting 64 watts, call it. Now that's 10 watts drive, so you're 88 watts. 15 watts drive, it does 100 watts there, but I've knocked it down to 10 watts drive. It does in 87 watts, which is pretty good. So yes, I might try tuning the RF capacitor on the input. So this capacitor down here, which is right. Okay, we're back. The camera fell off its mount, would you believe? So we're now back on air. Right, so this capacitor here, I'm going to try and tune that while we're looking at the output on the bit careful about the biasing at the moment, because obviously the biasing could cause excessive current to be drawn by the amplifier. So we've got two capacitors. We've got this capacitor and this capacitor, so I'm going to tune both of them. I'll tune this one first actually, and then this one second, and see what kind of RF power. I'll start with 5 watts actually drive, and then we can take it from there. Okay, so we'll just key up the transmitter now. We'll go on to the first capacitor, and then we'll just see what kind of output power we can get. So I'll just start adjusting the first capacitor now. I think we managed to peak it around about 65 watts roughly. Obviously as it's heating up, the RF power is actually declining somewhat, so we're just trying to tune it for maximum. We'll just unkey a second while that's running still. Right, key up again, doing 62 watts, 65. So I think I can peak it around about there. Don't think it's going to do any more than that. Just unkey for a second. Transmit again. 68 watts, 70 watts call it. Just tap that relay to see if we get a bit of so 70 watts. Right, we're going to go on to the other capacitor now, that plated RF capacitor. Just going to see if we can adjust that and see what we can get out of it. Okay, so that's 60, 50 odd watts, 65 watts. Just on key again. Let's see what we can get out. Going down again that way, so just have to try and peak it as much as we can. So round about there sort of thing. 65 watts. So if I'll just unkey, leave it to cool a bit because the finals are quite warm. Right, just key up again. Now it's cooled a bit, so you're looking at 65 watts. Just adjust it a bit more. There we are, 72 watts. And that's with 5 watts drive. Right, I'm going to increase the output power now on the drive radio from 5 watts to 10 watts. And now when I key up, let's see what power we get. 94 watts. So I'm happy with that. That's on 434 megahertz. So let's go back to, I think it was main. Right, so I'll try 435 megahertz now at 10 watts drive. Getting 93 watts there. Try 436 megahertz. We're getting 92 watts on 436. Just try it on 440 megahertz. 85 watts on 440. Just try it on 449 megahertz. 74 watts. Okay, so I'll take it down now to I'll try it at 420 megahertz. I'm getting 84 watts out at 420 megahertz. 430 megahertz. 90 watts call it. And on 433 megahertz, getting 94 watts. So that's as near as damn it, I think, as to you know, what we can get out of it. I think we've done pretty well, really. The fact that it actually works, you know, that's quite an astonishment. And obviously, key up, you can see the little relay plunger going in there as well. So that's worker. Just need to replace the fuse holder then at the back. So that's actually been quite a good purchase, really. Considering how much I paid for it, didn't pay much for it, based on the fact that the person who had it didn't really know how to test it properly. But it's obviously had some work done on it. The tanks have blown and they've been replaced. So somebody has done some repair work on it, and maybe something else hasn't quite worked after that, or they didn't have a supply big enough to provide the current needed to get 100 watts output. But as you've seen there, that seems to be satisfactory, seems to be working quite well. Back soon. Okay, so what we're going to do now is a spectral purity test. We're just going to we've altered the resolution, bandwidth and the visible spectrum, if you like. So I'll put the markers on. Now if I adjust the marker, which we can see up there in the top left hand sort of middle bit. Marker 1 is at currently 838 megahertz. So basically the top end, if you like, of the screen, just this end, is 1 gigahertz, and that's down to its minimum operating frequency. Take notice of that signal. That's just something that it picks up internally. So our transmission is going to be around about here at 100 watts. So when I key the transmitter up, we can see it coming up there in the middle. We're now on 100 megahertz per division, and the marker, which is the dotted line to the right there, this dotted line, that one is 838 megahertz. So if we were going to get harmonics appearing, they would appear more or less towards the right. The second harmonic would appear there, and we could just see a tiny little thing there, and as you can see, unkey, it disappears. So the transmitter carrier, so we're looking at obviously quite a clean output there with the look of it. So if I reduce that now back to, you know, where 2 megahertz per division roughly, we'll be able to see the transmit carrier at 100 watts there. So that sort of is a general rule of thumb. We've looked at, you know, obviously the spectral purity side of things, based on the fact that it's doing 100 watts, and if I turn it down to 5 watts drive, so it's doing 60-70 watts again, and we can see a little bit of something to the right of it, and also to the left, just tiny little amounts there coming and going. It's well below the carrier level. Now if I can put the marker, shift the marker to that, and see what that frequency is. So if I move a marker down there, we can see roughly what that peak's going to be. So that's 434 point, I think it says 35939 or something, when we're transmitting on 433 dead. So there's a bit of intermodulation product there, and it's sort of quite low down on the scale. Is that it's not something to be worried about. And but again, you know, when you're using an amplifier like this, you should really use, you know, sort of cavity filter or something of that nature, because amplifiers are quite dirty, a lot of them, unless they've got bandpass filters built into them, which this one doesn't have a bandpass filter in there, as you can see, but it is actually quite clean considering, you know, the output powers that are involved. But again, it's this sort of thing where you need to look at that after you've done a measurement. So if I increase the bandwidth now up to 100 megahertz per division, and then key the transmitter, as I say, the far right of the screen represents 1 gigahertz. We're getting a nice peak in the middle, but we haven't got any at this stage anyway. We certainly can't pick up the second harmonic there, because that lies just under the 1 gigahertz mark. It's twice the frequency. So we might use the other spectrum analyzer we've got down there shortly to have a look at the spectral purity higher up in the frequency range, sort of the 3rd, 4th, 5th harmonics that will be well into the gigahertz frequencies. I think it'd be worth having a look at that. But before we do that, I just want to test the protection circuit on the amplifier. So how I can do that is I can remove the BNC connector on the rear of the amplifier, so there's no output at all connected to anything, and then what we'll do, we'll key up and see whether the VSWR alarm trips. So there we are, look, it's tripped it. So that directional coupler that's in the rear down there has actually tripped it, and now we've got the VSWR alarm which came on and went off. If I do it again, so it stays on for about 8 seconds I think, and I can't key up while it's in that status. Once that goes out again, then we'll have a look at the current meter on there, and you can see it's not even drawing current before it trips, so that's pretty good. That tests that. So if a VSWR you didn't run it into an out, you know, a 50 ohm load, then presumably it would trip, which we just proved it there. It does trip, so that's good. That proves that the protection circuits are functioning, and obviously when I key up again into a 50 ohm load, we're getting the transmission. As far as current consumption is concerned, you know, at 70 watts, if I draw it so it's nearly doing 100 watts, then we're talking 20 amps more or less there on that scale. So just shows you the sort of high currents that are concerned when you're running these kind of things. So right, we'll have a look at some more detail now about its spectral purity. Right, we've now connected the directional coupler in, so we've got basically a sniff roughly about minus 20 dBs below the carrier power that's coming in, gets sniffed out this port here. So the main transmitter power goes through into the test set to be terminated, and then we've got a sniffed output at low level which we're going to feed to the Spectrum Analyzer. Now, a word of caution when using Spectrum Analyzers. What I tend to do is, just out of sheer devilment, is I like to measure the power, what's coming out, before we connect it to the Spectrum Analyzer. The reason why I do that is just basically for safety checks, because once you've overloaded the Spectrum Analyzer and you've blown it, that's it, game over. You know, you're talking mega expensive repairs and all kinds of calibration costs, various other things around it. So before you go connecting sort of anything into, you know, the Spectrum Analyzer, we've got to be very careful about what RF levels we're concerned with. Now, another factor is as well, amplifiers can run away with themselves sometimes. A variety of reasons why they can run away. Fault conditions can cause the output power to alter. Supply voltages can increase unexpectedly if we catch a knob on a power supply, something like that, and then the output of the amplifier might be 150 watts or 200 watts depending on what voltage we go to. There can be loose connections of RF cables, and when you're making your initial measurements, perhaps not all the power's there, but then when you do disturb those connections, suddenly the power jumps up to where it should be. So what we don't want to be doing is measuring an RF signal that's near the limits of what the Spectrum Analyzer can take on its input. Now, the HP 560E Spectrum Analyzer that I've got to the left, that I've just shown there, has a maximum rated input power of 1 watt maximum. So we mustn't exceed that at any point, no matter what. Now, I'm not comfortable with running Spectrum Analyzers with hundreds of milliwatts of input going into them. So I've got some choices here, depending, because we're dealing with 100 watts on UHF, and the sniffed output from this particular directional coupler, we need possibly to attenuate it, and I've got an attenuator there. But just to demonstrate that, if I disconnect, you might have watched Mark Almus wideband amplifier video where we looked at a metrology grade RF power amplifier that is a wideband 1 megahertz to 1 gigahertz 10 watt power amplifier, and in that video I showed about needing that headroom in the measurement, because even though at the time we were measuring, I think it was a couple of watts RF into an attenuator, and then we fed the output of that attenuator to the Spectrum Analyzer, the attenuation that we needed to provide to the Spectrum Analyzer had to have some headroom in it, and it was for good reason, because when we swept the frequency of that amplifier, between certain frequencies there was quite a bit of headroom after the attenuator between the maximum input level of the Spectrum Analyzer versus what the attenuator could provide. However, at lower frequencies, down at sort of a 1 to sort of 30 megahertz range, the output power was at least 3 times the output of higher frequencies. And so it wasn't wholly flat and linear, because we needed to do some biasing adjustments and also some tuning adjustments. And due to that characteristic, it meant that that particular frequency range, the headroom that was therefore available earlier at the higher frequencies, had gone. And so therefore the output power of the attenuator that we're using in that capacity would not attenuate the RF to sufficiently lower level where it wouldn't damage the spectrum analyzer. Fortunately, in my case, we didn't exceed the maximum input level to the spectrum analyzer, but we damn came near to doing that. And so it's very, very easy to do, and you can overlook things, you know, as I say, supply rails can increase in voltage or something like that, and suddenly you're doing an RF measurement at sort of the very extremes of the measurement capability of the instrument, and you want to avoid that at all costs. Spectrum analyzers are exceptionally sensitive instruments, and the last thing you want to be feeding into them is hundreds of milliwatts or even nearly 1 watt of RF power, otherwise you're gonna screw the instrument. So to demonstrate what we're going to do, rather than assume, because you can calculate these things, and obviously you know, we could have an amplifier here that's doing 100 watts at 432 megahertz. We're using a directional coupler which might have a 20 dB frequency response between, say, 200 to 1 gigahertz, and we then would get 20 dBs at that particular frequency range. However, if the amplifier is dirty and it's doing, say, 50 watts at you know, at on the third harmonic, which is in the gigahertz range, for example, then it could be the directional coupler has more of a coupling effect at that frequency. The higher the frequency that you put through a lower frequency coupler, the more chance of the coupling being higher in amplitude. So therefore, you know, at one frequency the coupling factor on that directional coupler is at a particular level because that's what it's designed to do. But then if we've got a high powered harmonic or a self oscillation that's occurring in the amplifier and it's producing many watts at the wrong frequency because it's gone into self oscillation, then that particular frequency being higher in frequency may couple across the coupler in a higher amplitude than is normal for its normal operating range, and then the level of that signal will be in excess of what the spectrum analyzer can cope with, and so therefore you can screw your spectrum analyzer without knowing it. So there's all sorts of things that you need to take into consideration. The best method before connecting to any spectrum analyzer when we're doing sample RF power measurements is direct measurement of RF power, and that's what we're doing here. We've connected the sniffer on the Marconi straight into the power meter, and we're going to look at the levels in real time. So we're not using maths, we're not using our data that we're getting from the labels on the equipment. You know, you must never assume that you know, that is a stated output. Always check yourself first. So we've got it on a 3 watts on the 10 watt scale, so that's full 10 watts maximum deflection. We've got the radio set to 10 watts on the power amplifier output, so we've got that amplifier on. So when I key up the radio now, if I then look at the power measurement, so there we are. So already we've got some RF power being measured there, look. So when we look at that, 500 milliwatts is there, so we're looking around about 200 milliwatts, between 150 to 200 milliwatts. So as you can see there, if I turn the amplifier gain down on the radio so that it's say doing 60-70 watts, then we're getting just over 100 milliwatts. Now, although the damage level, it says on the spectrum analyzer, is up here at 1 watt, at sort of that level, there's a fair bit of headroom to go there, and technically we could use that. However, if we go then to what would be the 100 watts level, we are getting quite close to round about, yeah, I'd say probably 25% of the rated maximum that the spectrum analyzer can take. So in theory that can be used, but I'm not comfortable with that. I don't like putting hundreds of milliwatts into spectrum analyzers. So what I'm going to do is I'm going to introduce an attenuator, an additional one, just to give us a bit of a safety margin. So this attenuator here, I'm not sure what level it says on it. I think it's a how many dBs is it? Something like a 6 dB or something like that. Yeah, I think it's a 6 dB attenuator is that. So we're going to use this RF attenuator, and we're going to obviously if it's 6 dBs, I just need my magnifier because you can't see that through the camera. Yeah, it's 5 dBs. So for every 3 dBs we attenuate the signal, we half its power. So this will give us 5 dBs of attenuation, so it'll be half and nearly 3/4 again. So that'll reduce the power down to almost negligible levels on this meter. So we'll just do that now. We'll connect this SMA attenuator. As well as that, this acts as a safety bridge. Should the you know, unexpectedly the RF power rise or something happens with the directional coupler, which is near on impossible, but if something were to happen, then this would be what takes the brunt of the RF first before the spectrum analyzer, and thus it will protect what comes after it. I'd sooner that burn out than a spectrum analyzer burn out. I'm always really cautious about you know, the spectrum analyzer. Okay, so let's just transmit again now into the spectrum analyzer. So now we've got a lot less power now into the RF power meter, I mean, not the spectrum analyzer. So if we look at the RF power meter, we're getting about 50 milliwatts. So halfway between 0 and 100 milliwatts, 0.1 of a watt. So I'm happy with driving that level into the spectrum analyzer, and that's what we'll do. Now we'll connect it to the spectrum analyzer. I don't like providing high levels of RF into spectrum analyzers for obvious reasons, because we're getting, you know, it's quite close. So as well as that, some instruments are only rated, when you read the manuals, for momentary operation at certain power levels, not continuous. So if we were doing long transmissions on this particular amplifier and we were near the 50% upwards maximum level that the instrument can take, it can actually cause long-term damage anyway, simply because we're transmitting for long periods of time into the test instrument, and therefore it can heat up, or there can be reduction in performance due to certain pieces of modules in there that can overheat, or semiconductors which can start being overloaded, and therefore they give spurious emissions. So, you know, we'll be really overloading the front end of the instrument. So that's why we need to keep the signals really low power for those measurements. Right, so we'll connect it up to the spectrum analyzer now. Just move a few things about here. So let's have a look at doing that by moving this. Okay. Right, so I'm happy with that. We've got our cable here. Connect up to there. So just make sure that it makes a good connection onto this end type. Get the thread started, because it's quite precision connector. And then we can look at the signals. Okay, so everything's nicely torqued up. Okay, so what I'm going to do now is I'm going to use the spectrum analyzer now to make a measurement. So I want to put in the frequency. I want to put in the start frequency, and we'll say we'll start the frequency at 1 megahertz, and I want to stop the frequency at, say, 3 gigahertz. Okay, so that's going to give us that. I'm going to go to the amplitude key so that when we key the transmitter we can then adjust the amplitude accordingly. So I'm going to key the transmitter now, and as we can see we're getting quite a bit of so we do have some harmonics that are there, as you can see. What I'll do, I'll turn the power amplifier down to about 60-70 watts and check it again. So we've got quite a bit going on there. Right, we'll put the markers on, and we'll just go through what the frequencies ranges might be. So that's at this resolution, that's at 1.73 gigahertz. We've got another one down there, so we might have to reduce the resolution bandwidth. So I can go into, I think it was the span, where was it now? Might be under resolution bandwidth. Let's have a look here. I think there was something under resolution bandwidth, auto cal, marker old, pre-run. It's not under those. Just need to look at changing the resolution bandwidth. Right, last span 0, span amplitude might be under there. Reference level, maximum level couple, normal reference. Right, I'll just see if I can find the resolution bandwidth setting, and then we can adjust that. Okay, so to select resolution bandwidth, we press the BW button, and then we get the resolution bandwidth auto and manual modes. So in auto mode, obviously when we transmit, we are getting the fundamental and then all the harmonics. But what I can't see in this noise floor here is any more hidden harmonics. So what we have to do is change the resolution bandwidth to manual, and then we need to reduce the bandwidth, resolution bandwidth, and as you can see the noise floor starts to drop. The trade-off of course is that you get a slower scan rate from left to right, so that's, you know, obviously 100 kilohertz, but we get more detail with the harmonics, you see, which we've got there. Now as we can see, we've got the fundamental there, and then with some harmonics here at different levels. So what we can now use is the delta marker to make a comparison between what is the fundamental, which is this, and the harmonics as well, and how far down in amplitude they are in comparison to the main component, the main tone. So what we'll do now, we'll use we'll go back to marker, and we'll go to marker delta. So what we'll do, we'll transmit, we'll key up the radio, we'll go to, obviously that's the frequency there roughly of what we're on now, which is this fundamental here. Obviously the frequency accuracy changes depending on how wide the spectrum is that we're looking at. The narrower the spectrum, the more accurate the frequency counter becomes, so that's something you need to bear in mind. So we'll have a look. The second harmonic I'm expecting to be double the frequency that we're measuring on the fundamental. So if we're on 433 megahertz, I would have expected that to be on 866 megahertz would be the second harmonic. The third harmonic will be double 866 megahertz again for the third, the fourth double that again, so on and so forth. This spectrum analyzer only goes up to 3 gigahertz, so I can't look at any frequencies above 3 gigahertz. So what we're going to do now, we're going to transmit, apply the delta marker, which will reference the fundamental, and then we'll compare it against the harmonics. Okay, so we're just going to make some more measurements now using the delta markers, and the harmonics. In order to get that detail, we just need to widen the, if you like, what we're going to be looking at, because prior to this measurement we're looking at essentially the entire bandwidth of the spectrum analyzer. So we need, one, to improve its accuracy, and two, to be able to pick out the second harmonic primarily, and then look at the other harmonics afterwards. So we need to adjust the start frequency. I'm going to change it to 400 megahertz because we know the amplifier works at 433 megahertz in this case. I'm going to change the stop frequency to 1 gigahertz. This will help improve the resolution bandwidth as well. We've already changed down to 150 kilohertz so that we're getting that more detail of what harmonics might be hidden in the noise floor. So what I'm going to do now is I'm going to key up the transmitter. We'll go to the amplitude markers, and then we'll have a look at the fundamental in comparison with the second harmonic. So we'll key the transmitter, and as we can see, we've got the fundamental here, and then with this harmonic, which is the second harmonic. So if we go to marker, we can actually do peak search or peak find. So basically we can just drop straight on it, and that'll give us the frequency. Now that's obviously the fundamental. This here is the harmonic, so we can select next peak, and then it'll show us what that is. Now it's showing us the frequency, which is double the fundamental. Obviously 433 megahertz multiplied by 2 is 866 megahertz, hence the term second harmonic or the second tone. So what we need to do as part of the specification measurement is we measure the reference being the primarily the fundamental using a delta marker, and we then compare the amplitude difference with the second harmonic. And so it's the relationship between the amplitude and how far down on the fundamentals amplitude the harmonic is, and that's where you see specifications where it'll give, say for example, the second and third harmonic minus 57 dBs below the fundamental, or 57 dBs down on the carrier, and that's an indication of how powerful those harmonics are in the system. So rather than in this case by selecting the harmonic frequency and then reading the level in comparison to the noise floor, that's a different methodology, a different measurement to what it is when we compare it against the amplitude of the fundamental versus the amplitude of the harmonic. It's the difference, the delta difference between the two. So how we get to that is we basically go to, in this case we go to next peak, or peak find, select marker delta, so it makes that the reference. The amplitude of the fundamental is now the reference point, and then we can then go to marker, key up the radio again into transmit mode, and then we can select that harmonic or whatever signal it is that we're wanting to pick out. And then once we get to the peak on that particular harmonic, which is very shortly once the resolution bandwidth catches up, then we can measure that signal. Just waiting for it to catch up. Let's have a look. There we are. So that's the measurement, minus 57 dBs below that frequency. Notice the frequency readout that we're currently looking at isn't the frequency of this, even though the ball's above it. It's actually the fundamentals frequency, but it's the level minus, in this case 57, is it 67 or 57 dBs? Just need me thing. Yeah, it's minus 53, sorry, 0.67 dBs below the fundamental is this point here. Now if we want to look at the frequency of the harmonic, then we just go merely to normal marker, and the measurement then changes to what the frequency of the harmonic is, which is 866 megahertz. Obviously that level is not the relationship between the fundamental and the harmonic, it's just merely the actual level of the harmonic in relation to the noise floor. So that is the measurement of the frequency, what is the second harmonic. There aren't any other harmonics that appear in between, so that shows that there's no mixing going on or anything adverse there. So the next thing to do then is look at between, well, 2 8 to 16, so I'll be looking at 1600 and 60 something megahertz will be the third harmonic. So if we then go to frequency, start frequency 1 gigahertz, stop frequency 2 gigahertz, now we should be able to look at the third harmonic. And so I'm keying up the transmitter now, and we've got a couple that have appeared in this sort of frequency range. Now, one thing to note with harmonics as well, you can get undesirable mixing that occurs in junctions of transistors, so it wouldn't be necessarily double the frequency where you'll get tones, but you can also get tones that are in between those frequencies, because it's a product of harmonics mixing within the junctions of the transistors, which then can give obviously mirrors, harmonic mirrors of the harmonics. So in other words, you get harmonics of harmonics, and you get all sorts of weird things. You know, sometimes depending on how dirty the amplifier is, you can get like a hedgehog appear on the screen, really bad. So it all depends on the amplifier. Okay, again, what we can do is just have a look at the frequency first of that harmonic. So if we go to marker, we've got something here which appears at whatever frequency this will be when it comes up. 730 gigahertz. So there's something at 1.73 gigahertz, and then there's something down here as well, again at 1000, what's that, something or other, 1300, 1.3 gigahertz. So there's something at 1.3 gigahertz as well as 1.7 gigahertz. So that's that. Now obviously this here is still a harmonic, but the actual third harmonic is a double again of 866 megahertz. So that's going to be this one up here. If you double the frequency, 2 8 to 16, and then double 66, which is 1200, isn't it, basically? So, you know, you've got 1700 megs roughly frequency. So this is actually the third harmonic as such in relation to the fundamental. That doesn't mean to say that's at 1.74 gigahertz. It will be a slightly different frequency that when we open that out, but at the moment, because we've got such a wide 1 gigahertz bandwidth, then the frequency accuracy isn't as good. But this is definitely a signal there, obviously, as you can see when I key on key, and then it'll vanish now. So that is still a relationship to the frequencies that we're seeing, but it can also be mirrors of harmonics as well, and the mixing process, and that's where you get those other filling tones as well. And so you get images of images, if you like. So then what we'll do as well, we'll select the 2 gigahertz frequency range now, and we'll start at 2 gigahertz and finish at 3 gigahertz to see what appears in that part of the spectrum. So I'm keying up again, got a couple of tones here, so we'll analyse those next. Now obviously, although we're looking in the 2 gig to 3 gig spectrum at the moment, and as I transmit now, you can see a couple of tones there and there. They're not actually the relationship with the third, well, they're not the third and fourth harmonics, because the third and fourth harmonics are basic, well, the fourth and fifth harmonic, should I say, is beyond what the spectrum analyzer can measure. The spectrum analyzer can only go up to 3 gigahertz. So for example, the second harmonic is essentially 866 megahertz, which is double 433, and then obviously the third harmonic is 1700 megahertz, roughly for the third harmonic, and the fourth harmonic obviously would be beyond 3 gigahertz. It would come out at 3,464 megahertz, so 3.464 gigahertz. This instrument only goes up to 3 gigahertz. So basically what we're seeing when I transmit, looking at the analysts we're currently looking at, which is 2 gigahertz to 3 gigahertz, these are products of mixing and other effects that occur in the amplification of the fundamental signal. These may be coming from the radio as well and being amplified up. Also it could be the mixing properties within the transistor die in the RF power amplifier final transistors, and depending on the quality of the transistors and the die can all have a detrimental effect on how they mix and perform with harmonics. But they are in relationship to both the fundamental and the harmonics. They're mirrors of mirrors, basically. They're mirrors of the harmonics and divisions of harmonics, both going up the frequency spectrum as well as going down. And they are products of mixing that's occurring between different frequencies, which has been emitted by the radio. So I've just unkeyed the transmitter there. So that gives you a little breakdown really of sort of harmonic measurement and how we do that. And if I then go back to the frequency menu and select 400 megahertz to a stop frequency of 3 gigahertz where we were before, we can then see obviously the ultimately, if we key up the radio, select the stop frequency, the start frequency at 400 megahertz. That's it. And so we can see the fundamental here, and then we can see all the different sort of tones right up to 3 gigahertz, but only 2 of those are actual direct relationship harmonics to the fundamental, as in divisions of, you know, multiplications of the frequency. And the rest of the ones that are in the middle of those are mirrors of the harmonics mixing with the fundamental, and they are then create mirrors of mirrors, so that gives you an idea of what to look for. But the harmonics, the prime harmonics, are in relationship of doubling the frequency of the fundamental. So, you know, obviously the second harmonic, probably the third harmonic, and then the fourth harmonic will be off here somewhere, which is beyond the limits of the instrument. And these little ones that are filling in between are mirrors of the fundamental mixing with the harmonics, and mirrors of harmonics as well. So it just gives you a little insight into doing those sort of measurements. Now obviously you can use a delta marker for that kind of measurement as well, and deal with that, which is pretty good. You know, you can do quite a bit with it. But you can also do bandwidth measurements and 3 dB points as well if you're testing the bandwidth of an amplifier. In that case we would use the output of a track gen into, say, that Calmus amplifier. They have a wide banded 1 gigahertz bandwidth amplifier. You would then feed the output of that amplifier then into this amplifier we're testing now, this microwave modules, and then we would then have a return signal as we've got there coming back, and we would then be able to measure, if you like, the performance bandwidth of the amplifier, which we can do, and then measure its 3 dB points to create its bandwidth. So that's another measurement that you can do as well, but that relies obviously on having a metrology grade amplifier that's capable of providing a fairly linear frequency amplitude response across its operational frequency range, otherwise your measurements are going to be off. So anyway, at least you've seen that working, and that sort of shows that bit. Well, we enjoyed that little preview anyway of what we were doing with the harmonic measurements. Obviously when you're testing high powered amplifiers of any degree, typically in excess of 100 watts, better to have a fan on, keeping it cool, because on long transmissions that amplifier is going to get really hot. Likewise, if you you're putting the RF power into a radio communications test set, the one I have here is rated to 150 watts maximum. This is only 50 watts below that maximum, so the test set's going to get pretty hot pretty quick. And to save the radio communications test set RF load from getting excessively hot or causing damage to the instrument with such high levels of power, it's always better to use an independent RF load, particularly on long transmissions if you're doing measurements or alignments, rather than terminating to the test set. The test set can cope with it, but it just improves the longevity of the test set by trying to terminate the RF power. This is a 250 watt load with a directional coupler on top there, which is obviously its RF cable then is obviously fed off to the Spectrum Analyzer, so that basically keeps everything nice and cool. The fan keeps the amplifier nice and cool. That is a 250 watt rated load, so naturally it can dissipate the RF power quite easily. We're only using it at roughly 50% or less than 50% of its maximum rating, whereas with the IFR Marconi radio test set, it had 150 watts rating, and we were putting 100 watts in. We didn't have much headroom left, so you need to think about longevity of instruments as well. And naturally as well, the DC power supply, the one I have, the 60 amp maximum power supply here, is fan cooled as well, using automatic temperature sensing, which is why you could hear the fan starting and stopping during the measurements. So that gives you a little rundown of using a directional coupler with an RF load to sample some power into the Spectrum Analyzer. We need to make sure, of course, we don't overload the Spectrum Analyzer's front end, because when we do that, by introducing a too high a level signal, will mean when we analyze the signal on the Spectrum Analyzer, it will be overloading the mixers in the front end of the instrument, and then it will be producing erroneous measurements on the screen, because we're just shoving too much signal into it, and it's going to struggle. So my advice is to keep it within the tens of milliwatts range. You don't want to be going for the 500 milliwatt level, the to 1 watt levels going into a Spectrum Analyzer, because all you'll do, it'll just overload the input to the Spectrum Analyzer. The scope will just light up with all sorts of interference. You may damage the instrument, cause an overload condition, and you're not going to get accurate measurements. So get the RF level really low down. I mean, don't forget, if a fundamental's quite a large amplitude, and you then home in higher up the frequency spectrum to what are small amplitude harmonics, when you introduce the amplitude key and change the input attenuator level to pull out the harmonics to increase their size for further analysis, what you're also doing, unbeknown to you, because you're not looking at it at the time, the fundamental, which is near the peak anyway, if you're introducing between 500 milliwatts upwards, is going to be nearly at the top of the scale anyway, no matter what. And so by altering the amplitude of the input attenuator to further analyze the low level harmonics, what you may be unbeknown doing is that you're also increasing the fundamentals level way above what it can cope with normally further down the frequency, and that will then overload the mixer in the front end of the Spectrum Analyzer. And then what you're going to get then is you're going to get weird measurements further up, and you're going to be looking for things that just simply aren't there because you're overdriving the Spectrum Analyzer. So it's one of the things that you've got to be aware of. Get the power down. We're not interested in measuring watts and what have you on a Spectrum Analyzer. What we're doing is we're reducing the levels down to tens of milliwatts, where you barely, even on a 1 watt scale RF meter, you're barely making the needle move. We want to be really aiming for about 0 dBm, no more, really 1 milliwatt sort of levels going in, maybe 10 to 20, maybe 50 milliwatts at maximum. You do not want to be putting in hundreds and hundreds of milliwatts into there. 500 milliwatts upwards, definitely a no-no, definitely not 1 watt. You want to keep it well below, well below those levels, otherwise you're just going to cause yourself problems. So yeah, it's been a good little video that, I think, and I've enjoyed looking at that. I'm pleased that the amplifier works. I'm just going to replace the fuse holder in the back, and then that's a known working amplifier. And it's been nice to do those adjustments and check the amplifier out. Fortunately, it looks like the only fault that's on it is what we've found with this bridged out fuse holder. Everything else seems to be fully functional, so you know, if it ain't broke, don't fix it, as the old adage says. And I hope you've enjoyed the video. I've certainly enjoyed making it, and if you like the video, please subscribe. It helps with the viewing figures, and I'll catch you in the next one. Thank you for joining me today. Catch you again. Bye bye. Okay, we're now joined by the technical manager, who's come to tell us about the pre-scaler module, which microwave modules also manufactured. And this is something I found in my cupboard, which I forgot I had actually, which is a 600 megahertz pre-scaler module divided by 10 pre-scaler module from Microwave Modules. Again, another one of their products that they make. I've a number of microwave modules, pieces of equipment and instruments that they manufactured. So again, another example of one of their products. I've used this quite a lot over the years. I must have had it best part of 20 years, so just keep hold of things like this. You know, they're quite rare to come across these days. Anyway, I think that draws the video to a close today. As we can see, the technical manager has exhausted himself of any more technical advice that we can give, and glad the amplifier works and is all tested and working using the various bits of test equipment that we've demonstrated today, and obviously the use of the directional coupler, which we can see there. And I think it's been quite eye-opening really to see that I've actually bought something that works. Because normally when I buy something from a radio amateur rally or online, more often than not when it comes it's not working and we have to repair it. So this is a very rare occasion where we've been able to demonstrate an amplifier that I've actually bought that I cannot believe works, and we've been able to go through the technical description, find some technical information, look at the circuit diagram, and then do some comprehensive testing on the amplifier by using obviously a radio on different modes, AM, FM and SSB modes, and measuring RF power. We've looked at dealing with the harmonic analysis as well on the Spectrum Analyser with regards to the performance of the transmitter and the amplifier's performance, boosting the transmitter's RF power, and the harmonic relationship between the second, third, fourth, etc. harmonics and the power levels that they are indeed aligned with insofar as the fundamental RF carrier is concerned. And I think by demonstrating the fact that we can measure high powered signals and take a sample and then obviously measure those signals in a proper manner, gives you the confidence then yourself that when using test equipment how to set it up and obviously make measurements yourself. So with that, thank you very much for joining me today. If you like the video, please subscribe, it helps with the viewing figures, and stick around on the channel. There'll be plenty more of these videos to come. I've got lots more equipment that needs repairing and designing, and there'll be more circuit analysis and obviously measurements and maintenance and repairs that we'll be doing on various bits of test equipment as well as radio telecoms equipment. And we'll see you in the next one. Thanks again. Bye bye for now.